Hello students, in this video we'll prove the Cramer-Rao bound, which provides a lower bound on the variance of an estimator that's unbiased. So let's suppose that x1, xn are random samples from a PDF with PDF f of x and theta. And we're trying to estimate theta, right? Our goal is to estimate theta. Let y, which is a function u of, it's a statistic of this sample, right? Be an unbiased estimate of theta. Okay. And I'd like to compare, I'd like to find a lower bound on the variance of this estimator y. Okay, good. So now let's make some observations. And so there's a couple keys to this. The first observation we make is this, is that 1 is equal to the integral over r. We're going to assume the variables are continuous. The same thing works in the discrete case equally well. Of f of x and theta dx. And so if I differentiate this equation with respect to theta, what will happen? If I differentiate this with respect to theta, d by d theta, this becomes 0 because the theta derivative of 1 is nothing, is equal to the integral over r. Again, I'm assuming that I can interchange the limits of I can interchange the integral and the derivative, so I need to put in some technical conditions, but we're just going to sort of figure out how this works in general. We'll worry about what conditions we need later for that. Okay? This will be partial with respect to theta of f of x theta dx, right? And now here's the key observation that we're going to use throughout this video, and that is if I have the log of a function, so if I have the log of g, for example, and I do the derivative of log of g, that is g prime over g, right? That's the logarithmic derivative. So I can write this as the integral over r of the derivative with respect to theta of the log of f of x and theta times f of x and theta dx, because the log of f of theta derivative will be f prime, which is what we have, df d theta, over f of x and theta, and I multiply f of x and theta to make sure those things cancel out, okay? So this is going to give me a new random variable over here, which is going to play a role in our analysis, okay? Now the next thing we know is we know that this y is an unbiased estimate of theta, right? Which tells me that theta is equal to what? Theta is equal to the integral over r, there's n samples over here, over rn, u of x1, xn, right? And then f of x1, theta, fxn, theta, dx1, dxn. Okay, great. Excellent. So now if I do the theta derivative of this thing, what can I say? So now I have a product. So we're going to use one other property of derivatives, of log derivatives, and that is if I have the product of a whole bunch of terms, right? If I have, say for example, I have g1 through gn, and I want to do the derivative of this product over here, the derivative of this product is equal to what? Is equal to the sum of the logarithmic derivatives, sum gj prime over gj times g1 through gn, like that, okay? J goes from 1 to n. We'll use that property of logarithmic derivatives. So that will tell me what? That will tell me 1, if I do the theta derivative of this relationship over here, 1 is equal to the integral over rn. There's no thetas over here, right? So I'm going to have u of x1, xn. And then what? And then we have the sum, j goes from 1 to n, of d by d theta of the log of f of xj and theta. And then that logarithmic derivative times f of x1 theta, f of xn theta, dx1 through dxn. Okay, great. And so now, that's great over here. So what can we say? The first thing we can say is the following. What I'm going to do now is I'm going to use the fact that I'm going to look at these random variables over here, right in the middle over here. So what we're going to do is we're going to construct a new random variable from this. So construct a random variable. Let z be what? Let z be the sum. J goes from 1 to n. The derivative with respect to theta of the log of f of x j theta. Like that. There's my random variable. Like so. And what do we know about the expected value of this random variable? Well, the expected value of this random variable, what do we know about the sum of the logs of all these things over here? The derivative of log of f of xj, f of xj dx is going to give me a what? It's going to give me a a 0 when we integrate it. So this tells me that the expected value of this random variable z is equal to 0, right? And therefore, and all these things are independent draws, right? So in other words, and then therefore, and the variance of z is just going to be n times what? It's just going to be n times the expected value of this thing over here squared, right? Expected value of the square x. Like so, okay? Great, because there's n copies, and so when I do the variance of the sum, I get n copies of the variance of any one of those things, and since the first moment is equal to 0, all I have to do is do the expected value of that random variable squared, where x is just any realization of these independent copies of these draws. Okay, that's what the variance of z is. Now, what can we say? I also have a relationship between what? Between the variable y over here, that's my variable y, and that's my variable z with respect to the distribution. So this expression over here, this 1 equals this, tells me that 1 is equal to the expected value of y times the variable z. So 1 is the expected value of y times z over here, right? Excellent. Now, what is the expected value of y times z? That's the expected value of y times the expected value of z. That would be if they're independent, but they're not independent a priori, plus the what? Plus the correlation of y and z times the variance, the standard deviation of y times the standard deviation of z, okay? So that's the expected value of a product in terms of the correlations, okay? Great. And so now what do we know? We know the expected value of z is what? The expected value of z is equal to 0. So this term over here is equal to 0. That term is gone. And so what we just proven over here is we just proven the correlation between y and z is equal to 1 over sigma y squared, sigma z squared. If I square the correlation, I get this right over here, because that says that 1 is equal to sigma y 1 over sigma y sigma z is equal to the correlation rho yz. So therefore, if I square rho yz, I'll get 1 over sigma squared and then sigma z squared. Okay, excellent. Now what do we know about correlation? We know correlation is always less than or equal to 1 when I square it, right? So this expression is less than or equal to 1 over here. Great. And that says what? That says if I rearrange this inequality, that 1 over sigma z squared is less than or equal to sigma y squared. And of course, that's the variance of the y estimator, and that's the variance of the z estimator. But what is the variance of the z estimator? We know exactly what it is. This is going to be 1 over n expected value of the square of the theta derivative of the log of f of x theta squared, like that. I need one more parenthesis over here to close the expected value, is less than or equal to the variance of the estimator y, the variance of the estimator y. And this is called the Cramer-Rao bound. Which says no matter what the unbiased estimator you choose to estimate your parameter of theta, the smallest variance you can get is given by this expression on the left-hand side of this inequality. And this expected value over here without the n, so if we look at the expected value without the n over here, what this is called over here, so this quantity over here, this expected value of the square of the theta derivative of this thing is called the Fisher information. That's called the Fisher information. And we'll see examples in further videos about how we can use how the Fisher information occurs in the study of asymptotic properties of the maximum likelihood estimator for any given parameter. Thank you very much.